Good morning, dear colleagues. I suggest starting the plenary session. In the program, there are 7 reports today. So the first report and the first speaker, Nazarov Airat Akhmetovich, ultrasonic welding of metals, equipment, modes, structure, and mechanical properties of joints. Thank you, Sergey Valeryevich. Good morning. Deeply respected colleagues, first of all, I would like to thank the organizers of this wonderful conference for the possibility to speak with my report at the conference. And second of all, I would like to thank my co-authors of my research team, as well as the Dorozhny Vasily Sergeyevich, the head of the organization Ultra Resonance. And I would like to note that part of this work about ultrasonic welding of metals is supported by the grant of Russian Scientific Fund. Ultrasonic welding of metals concerns the method of welding of metals in solid phase. I will start enumerating these methods, and then we will pay attention to the core of this method, the mechanisms briefly, about the equipment used, different modes, and also I will tell you about the results that we got by welding copper, nickel, and titanium, as well as about microstructure and strength of joints, and also about molecular dynamic joints. So one of the most famous methods of joints are welding with a burst or welding with friction, and it has the following types: are linear, rotational, as well as inertial, and ultrasonic welding. At this point, I would like to note that 3 out of the enumerated methods are widely used and researched at the institute where I work, and especially the diffusion welding is deeply researched, which is used in aviational building. Ultrasonic welding is quite a new technology. It developed in the middle of the 20th century with the help of the waveguide, which presents as a part of oscillation system. The metals press to each other, and the top and the welding tip make the sound oscillations, and there appears a friction process. So first of all, it's it's about a harsh surface that appears, and there are zones of catching which enlargen, and at the end there is a deformation of movement which causes diffusion as well as diffusion processes. And of course, it can be violated by high temperatures. The main parameters of welding are the amplitude of oscillation, the static welding, which presses the patterns to each other, can be from hundreds of kilograms to 10 hundreds, and the time of the welding can reach from 1 to 3 seconds. As a combination of these all parameters, we have the energy that defines the welding zone, and this is the main characteristic. The welding quality, which the welding quality depends on. And of course, it depends on exact equipment and instruments which can affect the quality of the welding. Ultrasonic welding has a range of advantages. First of all, it's a high speed, so the welding can be maximum some seconds. And it's also has a low energy wastes, and there is no protection from gas environment is required. But of course, there are also disadvantages, particularly it's about the strength of the joint. It's not as high as by diffusion welding. Nevertheless, the joints cut in ultrasonic welding can get the strength which is obtained by pointed welding, pointed contact landing. Each technology has its branch of use, its purge, and it can be used in electronics, electric technology, and machinery. This technology is called ultrasonic consolidation. It was invented in 2002, and it's one of the additive types of technology. So there you can find a roller which has a hard surface, and it can flatten or roll the leaf, the welded leaf, to weld the metal plate, or foils to the basic. And further, layer by layer, after welding, you can observe freezing. And one of the methods of employment of this technology you can see is some satellite heat exchanges invention and production. and it was by Fabrisonic company, was also produced very famous satellite. You can see the hardware of the ultrasonic welding. So you can see the press as well as the welding waveguide, and to control the parameters, the main parameters, which is the amplitude of oscillation, is a vibrometer. So three metals have been tested. It's copper, nickel, and titanium. And the next slides are presenting the patents which are received with the help of ultrasonic welding. They are made the following way. They are overlapped to and squeezed with the help of spring press, and the microstructure of these joints is pictured on these compounds, and the main element is not a very thick layer, um, where you can see the ultra fine structure, and the microstructure or microstructure also violates. And the rest parts, the microstructure is unchanged. You can also see the EBSD method, which shows that at the area of welding seam, there happens recrystallization, which causes the ultra fine grain structure. And because of the oscillating and high-speed deformation, there appears a formation of the developed structure. And in comparison with the original leaf, the spectra is changed. We can also see the cut of copper joints, and in the area of the welding seam, we can see about 20% micro wear, and the micro strength is about 1.5 times higher. And dividing the maximum efforts at which the destruction of this joint happens, we have counted 51 megapascals. First, you may think that it's not really high, but in fact it's higher than the standard figures tested before. The second test is on nickel. The maximum number of experiment has been done with the following kind of patterns. So first there were the pieces of leaf, and then the discs of ultrafine grain, which has about 0.5 micron size of grains. So it has been done in order to compare the microstructure and strength of the joints for different structure, ultra fine grain, and a wide high grain. And we can see the two different kinds. Two different kinds, the industrial spreading as well as ultrafine grain spreading. So we observe in both cases of copper and nickel, not very big differences. But in the welding seam, there is the same fast deformation processes, including the high friction. We receive ultrafine grains. And we found out that in the grains which were close to the seam, the number of them has grown. And there's only one thin layer of ultrafine state. But mainly what happened is the intensive growth of grains. And in recrystallized grains, there is a developed structure. And it's also interesting that in spite of this, the strength of the joint with nickel is way higher. It starts from 1000 newtons. And you can see the difference, about 40% of ultrafine grain nickel higher. And when we have the welding by pressure of initial ultrafine grain, the strength of the joint is much more higher than if we started with large or high fine grain. Nevertheless, the usage of ultrafine grain state for welding can be used by ultrasonic consolidation. And the next one is the titanium joint. And the hardest was to get the titanium joint. And even some professionals who work with titanium said it's hard to get it. And we discovered that one needs higher amplitude, higher static pressure numbers, and the timing was higher. And this is what we have received, the microstructural joints. Of course, you can see some defects at the edge. So the higher pressure, the more deformed the surface is. And we also get the thermal mechanical influence. And we concentrated on the research of this very area and the microstructure which derives in this area. So we have taken the industrial leaf of titanium, But anyway, so we can see that grains were grown on this leaf, and the leaf was deformed, and microstructure was developed there. The detailed research of the microstructure and structures of the following area shows that the texture differs from the initial leaf and the one that comes after welding. Now you can see the spreading of disorientation of grains, as well as the axis of the disorientation are concentrated in these zones. So 1, -1, 2, -1, 0. So all these three criteria say that the wide grains were formed in the process of beta alpha. And in this beta cell state, there was a plastic deformation and a good joint was received, more plastic titanium. And when cooled, there was the opposite alpha beta transformation, and thus we have such structural state. So it turned out that this kind of change gives a better quality titanium, and you can see the cuts of the titanium. There are two atom destructions, and depending on the mode of the welding, there can be different kind of destructions. And the maximum strength that we can observe on the cut of the titanium joints, it's about 83 megapascals. Thus we can see that in the process of ultrasonic welding of different metals, there are different processes of structural transformations caused by intensive influence, and it's interesting to find out some definite mechanisms of structural changes. Consequently, we have researches in the molecular dynamic modeling. There are three systems here. There are two copper blocks, and to model the rough surfaces. We can also see the pressure with a moving change. And these red lines are the thermostats to reflect the warmth, the heat during the deformation. So we can follow disorientation or vice versa, the absence of any impact of any contact. And we can also see the configuration systems of welding in the process of modeling. So the red lines show that these are the defects of the package. Thus, there was a now partial dislocation, which was developed from the surfaces of the cores, and there is intensive regeneration. And the plastic deformation, and we can see that there is no complete closure of pores with the amplitude at 8 nanometers and a pressure of 270 megapascals. At the first stage, we could follow we can observe intensive dislocational activity, and it's a high activity. And in the following, it will go through because they are the boundaries of the grains. And we can see a higher elasticity in this zone, in the area of welding, and a faster closure of pores. And the spreading of temperatures at modeling. The system was split into layers. You can see the first model and the second model with initial spreading, and the different colors are about 6 different cycles of an influence with different temperatures, but it's non-symmetrical. In the top block, the temperature is higher. But even after the migration of the grains to the upper state, we can see unequal, unsymmetrical spreading of the temperatures in this initial state. And these are the main conclusions that we have obtained. I would like to note that mainly it's that we can weld at the ultra fine grain state. It gives higher quality joints. There are some peculiarities about this orientation, and secondly, the spreading of temperatures at ultrasonic welding can be non-symmetrical, so the higher layer will heat way faster. Thank you for your attention. And I also like to add to demonstrate this slide as a net for the conference. Thank you for your attention. It was a very interesting work. The questions concerned the details of process realization. So in modeling, it was shown that the counting was not more than 600, 700 kelvins. The question is the following. Did you assess, at least integrally, the temperature that is developed? Of course, we tried to assess the temperature at welding the titanium. But there can appear destruction of the thermocouple. we have a lot of data. It depends on the equipment, on the area. As for example, of 650 of copper, and with the titanium, it can be even up to 900 degrees. We consider the center of the object. Haven't you done the pressure lower? You could use the harshness of the connecting surfaces or reducing of the pressure numbers. Surely the pressure influences, and there is the maximum. If we build the strength, the dependence of strength, we can get the maximum connected with it. A too high pressure can influence the quality. So we have found it for the equipment. So what should be the amplitude concerning the surface, the split boundaries? Usually in such equipment, we use cross waves, and they make a cross amplitude oscillations. And we require to make the movement of the connected parallel surfaces. Do I understand right that while welding, the pressure comes from the outside? So are there any edge numbers or ratios concerning the frequency? So the frequency doesn't play a main role, and usually they're used about 20 kilohertz of frequency in industry. And the pressure is mainly required to get the catching the connection. So we haven't changed the pressure number.
Jing XIE
У нас все
как будет? Доклад Modeling the spatio-temporal evolution of bone-implant interface stiffness via stochastic numerical approach. Так. Что? Сети, да? Hello? Next report, Jing XIE.
Okay, good morning. May I speak now?
Yeah. You can.
Okay, thank you. Good morning, dear chairman and professors Moving, and also professors and colleagues from Komsomolsk. And let me share the screen. Okay. Okay. Okay, good morning. It's very great honor to be here to share my current research work on the modeling the spatial-temporal involution of bone implant interface stiffness via a stochastic numerical approach. Before discussing our work, please allow me to introduce Beijing Institute of Technology briefly. So BIT was founded in 1940 in Yan'an, Shanxi province, and was relocated to Beijing City in 1949. So in 1952, the school was renamed Beijing Engineering College, the first defense industry university in the PRC. In 1988, the school was renamed Beijing Institute of Technology. So now BIT has more than 3,400 staff, including 23 academicians and 18 professional schools. So the BIT aims to develop students as leaders with ambition, wisdom, innovation, and sense of duty. And me, I'm an assistant professor of Department of Engineering Mechanics and the School of Mechatronical Engineering in Beijing Institute of Technology. So my research interest focuses on the impact dynamics of materials and structures. I was graduated from the Institute of Technology in 2010, major in material science and engineering. So after that, I went to France for pursuing a PhD degree from the laboratory of Lenskiy and in Saint-Lyon. After that, I went to TechNew for postdoc research as a Professor Daniel Rito's group in TechNew Israel Institute of Technology. After that, joined BIT in 2018. So the current work was a collaboration with Professor Daniel Rito in TechNew and also Dr. Chantal Yuna from Tel Aviv University and Associate Professor Fouken Ali Shah from University of Gothenburg, Sweden, and Professor Anders Palmqvist, also from University of Gothenburg, Sweden. So today's talk contains 4 parts. The first is introduction of this project, then introduce the materials and methods used in this work, then its results and discussion. After that, it's a short conclusion and the perspectives. Okay, the first introduction of this project. So since the discovery in the 1960s, osseointegration has revolutionized the fields of medicine and dentistry. The osseointegration relies on the biomechanical integrity of the bone implant interface and all the contact quality between the bone tissue and the bone implant material. So peri-implant healing is a dynamic process, and this healing process involves an immune response, angiogenesis, osteoprogenitor cell recruitment, bone formation, and bone remodeling. So this is a complex process. The true nature of the bone implant interface thus remains open to interpretation. So from the spatial perspective, the bone implant interface titanium implant has several scales. On the macro level, osteonal lamellar bone is found adjacent to the implant surface. On the micro level, in addition to osteoclasts in resorption pits, osteocytes are found embedded within the mineralized matrix and make direct contact with the implant. On the submicron level, groups of mineralized collagen fibers are aligned parallel to the implant surface. To move to the nano level, appetizer platelets intermix with irregularities on the implant surface. Individual collagen fiber exhibits a characteristic 67 nanometers crossing banding pattern, and no interview layers exist between bone and the implant surface. And the last, on the atomic level, correlative spatial and chemical tomographic imaging reveals intermixing of calcium from bone and titanium species. On the other hand, from a temporal perspective, the implant and the bone interface has a time history involving process. So bone formation occurs both from the osteomer powder, and this was created during the implant bed preparation, as well as from the implant surface. So these two distinct processes are termed distance osteogenesis, in short DO, and contact osteogenesis, respectively. So for DO, osteogenic cells line the old bone. On the other hand, for the contact osteogenesis, osteogenic cells lines the implant surface. So in briefly, for DO, which means the bone formation from the old bone to the implant. For the contact osteogenesis, the bone formation from the implant to the old bone. So in DO processes, the secretorily active osteoblasts anchored into their extracellular matrix by their cell process become trapped between the bone they are forming and the surface of the implant. So only possible outcome is the death of these cells. In contact osteogenesis, the novel bone is formed directly on the implant surface with a cement line in contact with the implant and is equivalent to the osteonal interface. So bone healing is often assessed experimentally. However, these experiment studies largely depend on the selected model, thus the sensitivity of the test methods and their limitations. For those regions and the expectations from the experiment investigation, so it's often combined with a numerical modeling in a so-called hybrid experimental numerical approach. There are two often used numerical approach. First, called the macro-scale model. This model is a homogenized microscope model in which the bone structure is replaced with a solid equivalent one. On the contrary, for the microscale model, this model in which the minute microstructure details are included. So these two complementary approaches are usually applied to bone analysis, however, without addressing the interface. So appeared a simple yet physically informed micro to macro model that could easily be implemented in numerical study of the bone implant interaction is still missing. So in our current study, we aim to develop this stochastic spatial and temporal bone implant interface model. Next is the materials. Before creating the metal, we have to create a few assumptions to simplify the modeling work. So assumption 1, the minimum and the maximum Young's modulus values for the mineralized collagen fiber MCF unit cell are obtained from a sub-micron level model, where MCFs have been analyzed as straight cylinders. These cylinders whose diameter 100 plus minus 5 nanometers. And these cylinders randomly orientate with a dispersion of plus and minus 15 degrees with respect to the long axis of the cylinder. A second assumption, the kinetics of bone healing are assumed for each direction of the peri-implant osteogenesis, the CO and DO. So CO extends away from the implant surface and progresses at a rate about 30% faster than the DO, with rates set initially to 3 micron per day and 2 micron per day, respectively, which means seal from the implant to the old bone. The progress rate is 3 micron per day, and from the old bone to the implant is seal, the rate is 2 micron per day. So seal is faster than the DO progress. So the assumption 3, the kinetics coupled involution of the bone implant interface stiffening is assumed to start from the most compliant initial state, day 0, up to the stiffest state in steps of 10 days. Because the healing time for the implant usually takes up to about 6 to 12 weeks. So here are a few figures to show the involving bone implant interface model. Here's the pointer. Okay. So this is a bone implant interface model, and the model size is in length is 250 micron with a square cross section 50 micrometer and 50 microns. And this is a cubic model. Now here this set is adjacent to the implant, and this set adjacent to the bone. So the seal is from the seal osteogenesis process from the implant to bone, and the deal distance osteogenesis from the bone to implant. And this finite model divided into these structures with 1 times 1 times 1 cubic microns, and this cubic cell represents a unique cell of mineralized collagen fibers. And here shows the boundary conditions. Two sides, this side close to the bone is fixed and the boundary condition, and this side near the implant we apply 1 megapascal tension force, and all these force is free boundary conditions. And this figure schematic shows kinetics of the peri-implant osteogenesis cross-section, which means at the day 0 is the initial most soft state between the bone and the implant, nothing here. But after 20 days, at day 20, they have the seal and deal, the bone, the new bone is grows to meet each other. At day 50, the seal and the deal front meet at here. After that, the whole interface becomes stiffer and stiffer until the final state. So here shows how to determine the Young's modulus for this spatial and temporal involution model. As we can see, as a day 0, it's a minimum Young's modulus state, and after 10 days, because the seal and deal, they close to each other, so they are become stiffer, 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 stiffer. So until day 50, the seal and deal fronts meet each other. As the two ends, they already reach to the highest value of Young's modulus. This is, we call it a before closure. So after the gap closure, then the lowest parts become stiffer, stiffer, stiffer. So the average of Young's modulus reach the maximum states after 100 days. These two figures show the random material distribution for different layers of interface on day 50. So we can see on day 0, all the lowest values of a Young's module randomly distributed in this model. And day 50, some highest Young's modulus appears at the two ends and also in the middle of this seal and deal front. So for this day 50 model, we just show several cross-section layers. Even as each layer, the Young's modulus material properties also randomly distributed in each layer. But on the average, as long distance, active distance of this model, They show as two ends, they have the higher value, as CO and DO, they meet at this middle point, they still has the lowest value of Young's modulus. So with this model, after apply 1 megapascal tension force, let's look at what we got from this model. And this figures shows the involution of epsilon xx strain distribution over a 100-day period at such growth rate. We can see the longitudinal strain varies with time and involves over the 100-day period. We just zoom in the day 50 results. The 3 cross perpendicular planes. We can see no matter which plane, the heterogeneity is evident in all 3 planes. So at the first step, we elaborate a representative unit cell with homogenized mechanical properties that depend on the local mineral content or mineral volume fraction, and to a lesser extent on the interactions between the mineralized collagen fibrils as a function of their geometry and overlap. So next, this representative unit cell is multiplied to construct a typical macroscopic bone implant interface with graded properties that are modulated according to the biological information at hand. So the present approach allows tracking each cubic micrometer of bone throughout the process of peri-implant osteogenesis, the heterogeneity distribution of the mechanical properties, and the involution spatially within the bone implant interface region and over time. So the heterogeneity intensifies from day 0 to day 50, then decreases gradually until day 100, where the distribution is quite narrow and is centered at roughly 40 microstring here. So at day 0, you can see it's more general, but after that, when the healing process starts, the heterogeneity intensifies. This peak shifts from the 600 microstring to the 40 microstring, which means the bone implant interface undergoes a dynamic involution from compliant to stiff. And here, this value here probably is due to the discontinuities distribution of Young's modulus we assigned in this model. So while bone turnover has not been addressed in the current work, bone remodeling approaches based on the strength, the famous Wolff's law, can be easily incorporated. The strength experienced by bone, deformation is between 30 to 700 microstring range, are not sufficiently high to induce a significant anabolic effect. However, it is important to note that tensile stress of only 1 megapascal is being applied. So if you apply a different force or a different type of force, you may get a different result, and this result may induce bone remodeling or trigger the bone damage. So the findings report here concern the mechanical stiffness of the bone implant interface, and as such, they are independent of the geometric dimensions of the current model, but depend on the bone healing kinetics that were assumed. We calculate the result stiffness. This value was obtained by applied stress divided by the macroscopic nominal strain. We can see from the left figure, the sigmoidal structure is obturned, and a distinction can be made between 2 steps, open gap and closed gap. So upon the point of gap closure, the result stiffness does not increase significantly. So this region, we call it an open gap zone. And after the gap closure, the result stiffness increased significantly and gradually levels after 100 days. We also calculate two additional cases, which means we have different kinetics. So the blue curve is the CO faster than the DO. And the red curve means the CO and DO has the same rate. But for the yellow curve, which means CO progress slower than the DO. So three different kinetics. We can see for a fixed initial length, which means 250 micrometer this model, the rates at which CO and DO occur do not only influence the time needed to close the gap. We can see for this CO and DO, CO faster than DO, only 50 days to close the gap. But if they are similar at the same rate, which means longer time, if the CO is slower than the DO progress, we need 84 days to close the gap. But also these kinetics affect the slope of bone stiffening, which means the slope here. During the healing process, illustrating the purely kinetic nature of this problem. When we look at these curves, it reminds us the percolation hypothesis in the physics. So we can interpret the results from this perspective. At day 0, the scene is dominant by confined MCF unit cells that may be assumed to be interconnected in any random network. So as time elapses until gap close, those confined unit cells diminish in numbers, leading to assume the state of this connection close to the percolation threshold. As time elapses, stiffer cells appear in increasing numbers and form a strong connected network. So this gradual substitution of confined unit cells by stiffer unit cells and their spatial distribution are deemed to be the responsible factors for the observed percolation phenomena. So from a clinic perspective, the present results are relevant for the clinical dancing communities in two aspects. The first relates to the submerged initial healing time. Within the limiting assumption of the model, it appears that the minimum upon time is precisely that required for gap closure between the CO and the DO fronts. So the next, noting that the present characterization of the interface can be used to model any kind of interface and load combination in a bone dense implant system. So one can now tackle implant stability issues, both primary and secondary, and also as a reflection of the interfacial physics and the mechanical conditions over time with the resulting implant and micro movements. So the last short conclusion and perspective. So in this study, we propose a relative simple spatial and temporal mechanical model to bridging the MCF unit cell and the macroscopic bone implant interface. The linear elastic stochastic finite element model reveals a highly nonlinear temporal involution of the interfacial stiffness with two distinct periods, gap closure and gap stiffening. Priorities a complete closure of the gap between the two para-implant bone formation fronts. The interface possesses small stiffness. Following a gap closure and subsequent stiffening evolves into a much higher stiffness. So this stiffness transition is reminiscent of percolation transition whose threshold corresponds to the gap closure. So that in the future, the further investigation can be include experimental validation of the model, modification and optimization of the current modeling approach based on quantitative experimental data, and the introduction of implant surface roughness and the impact thereof on the biomechanical integrity of the spatial temporal involving bone implant interface. So thank you for your time, and if you would like to further discussion, welcome to check our website and also email me. Thank you again.
Thank you, Dr. Xie, for excellent report.
Thank you very much.
Who has question? Good morning.
Good morning.
I'm Alexei. So good morning. I'm glad to see you here.
Okay.
My first question is, why did you choose the tension loading in your model, and why did you choose the exact value of 1 megapascal?
Yeah, so this is first version is model. So for testing the model feasibility and the feasibility and the reliability of model, so we just select a very simple tension force and also 1 megapascal as a unit pressure to evaluate this model. Of course, in the conclusion part of perspective part, I see this model can be applied any type of force like tension, torsion, compression, even the dynamic loading. So, and also different values of this force and pressure. So at this first step, only choose the simplest one. But in the future, we could apply like more types of force to see the bone implant interface response to different loading condition, to different strain rate loading.
Thank you very much. Thank you for
a
very interesting presentation. My second question was about the ability to apply the loading that can differ in time. So, but you answered this question. So, thank you.
Thank you for your invitation, and thanks for allowing me to attending this conference. And it's my so excited to communicate with you through this way. Hope next year or sometimes we could meet face to face.
So it'll be good. More questions? One more.
Can I ask you about the stochastic approach? Because as I understand, this is typical deterministic kinetic model. Where is stochasticity in the approach?
Repeat, please.
My question is about stochastic approach. As I understand, there is a deterministic kinetic model you use. Where is stochasticity in your model?
Gaussian distribution of these Young's modulus. In each layer, we choose like 10 classes of Young's modulus. Very simple, from 1 megapascal to from 1 gigapascal to 30 gigapascal. So the minimum is 1 gigapascal, then the maximum is like 30 gigapascal for the bone tissue materials. So we divided this range into the same intervals like 1 gigapascal, 3, 5, 7, 10, 11. And we just randomly to distribute this value to this single layer and follow a Gaussian distribution. So in each layer, it's a Gaussian stochastic characteristic, but on average, from the two ends to the CO and DO frames, it follows this smooth lines. It also involved with the time. I don't know if I answer your question clearly.
Thank you very much, Dr. J.
Thank you.
Следующий докладчик.
Проверка.
The next report is going to be presented by Maxim Alexandrovich Lenskiy, Organoboron polymers as universal modifiers of polymer composite materials. Good morning, dear colleagues. I come from the city of Biysk. I would like to tell a little bit about that city. Many people have already been in Altai region. Biysk was founded in 1709. And as Tsar Peter I wanted to manage the basin of the river, he founded the city of Biysk. So now Biysk is the second main cities of Altai region. It's a huge industrial city which solves many problems concerning defense, and the defense capabilities. Yeah, you can see the doctors of chemical science, Belosov Alexander Mikhailovich and Tolstikov Genrikh Alexandrovich, doctor of chemical sciences, professor of the Russian Academy of Science. So the modern conditions of technology development give us an opportunity to work with new joints, new composites. So it can be the synthesis of new polymers or modifications of well-known ones. So from the point of view of modification principles of polymer composite materials, there are two approaches, a physical approach and the chemical one. The further part of the report is going to be devoted to the chemical method. Everybody is aware that everybody is aware that boron is the fifth element of the Mendeleev's chemical table. So there is a lacuna formed, which can join atoms by molecular mechanism, but as well as it whole group, and the connection is so strong that the reaction with this small joint can keep the strength and will not distract. So these connections are quite strong. So the modern composite materials are quite compound, and the main problems while forming it is to combine something that is impossible to combine. As these are the materials of different nature, the cooperation is highly important for the ready-to-use productions. So knowing in advance different abilities of phenols, and most importantly for any composite, it's the ability to work out different ways these polymers. You can see the common scheme of synthesis of polyethers or polyethers, and under the influence of formaldehydes, they can give us more than about 35 different kinds of joints, which hasn't been researched before. In the industry, polyethylene and polymethylene are widely used. This polymer today is used in a range of different fields. I will tell about them a little bit later. But mainly concerning the materials of this analysis, you can see that at thermal acid, the polymers are quite resistant to the temperatures. So they polymers also work with sulfur systems as well as resin systems. Thus, we have the cooperation with the components of solidation, we can see the polymer friction composites in the next slide. And we will see the factors in different fields. Surely there is a depression, the squeezing and the heat. And of course, these polymer composites require to be different properties. You can see the modification results. Now we can see the composites of asbestos-free with asbestos-free and asbestos compositions. So to say, this material is usually used for the cars with low loading masses, and asbestos-free composition are used in the system of drag acceleration, or so-called application of brakes. And it is used as well in the brake pads of cars. It couldn't be heat higher than 300 degrees. Thus, we think that there was the spreading of heat, and the modification was held with a well-known of 100% of composite with a boron-based polymer. You can see the essential changes in the molecular net. And these processes give us to suppose that there can appear 3D nets. So we can see the experiments on the polymer composite curves after the temperature influences, and the highest effect is observed on the composition including asbestos. The given data led us to avoid such a process as the refusal of brake pedals when going down the hill, for example. The conclusions of composite modifications. So the further experiments are undertaken not by our team, but nevertheless, these are the composites made by the scientists from Yakutia. They also added polydispersed powder. We can see the reduction of thermodynamic properties, and the polymer spreads in polyethylene, high molecular one, and we can see the difference by the sizes of these particles. And this is the method of modification that they have chosen. And there are interesting results of growing of the strength. So the boron-based modificators strengthen the material. In the top, it's about 30-35% of strength. There are very interesting experiments in tribology where we can see that when the modification field grows, the coefficient of friction is reduced and the intensity of wear is also reduced. Consequently, the polymer is the modificator of the wear. So it means that it can make the wear resistant properties higher. I personally think that there is a polyhydrogen on the surface of the material. So generally polymethylene of triphenyl ether acid is the effective modificator which can help to increase the stiffness borders. One more common problem, global problem, is wide usage of them in glass plastic in atmosphere conditions. So we can see the ultrasonic emission that influences and destructs the joints. So there can be applied some coating, for example, to paint these materials, which is not always comfortable. The second is to modify their surfaces. So these can be solutions of the mentioned problem. So there are different works devoted to it. Of course, if we talk about the modification, it's the materials or antioxidants which the effect of which doesn't give to distract the polymer. And the second one is when they observe the ultrasonic emission and don't let the material get distracted. As a rule, they're low molar ratio used in the process of usage. They can be cleaned away by some weather conditions, atmosphere conditions. And again, going back to the boron-based polymers, in the slide you can see the results on strengthening one-directed epoxide composites. The maximum growth is 13%, 14, 16%. It is connected with the epoxide composition, which is widely used and works on the edge of its strength. A more detailed explanation for the following slide. Once Novosibirsk's firm ordered some researchers. Of course, we agreed to take this order, but by the deadline, 2 of these patterns were not ready, and we decided to replace them with the patterns of boron-based ones. So this material is non-resistant to so we can see that the strength is lowered. And so the polymers, which I have mentioned, they modify and grow, make this product strength to grow. but we couldn't make a range of products by winding. And so there were 3 recipes chosen for the experiments. So one of them, as you can see in the picture, is post. For high voltage equipments, and you can see the results from all the mix of absorbers. A big surprise for us was the boron-based polymers resist to any kind of disintegrating or corruption of the system. And also there were 2.5 hours of UV rays influence. The question, how do the boron-based polymers influence so badly on the strengths, is open. Now we can suppose that the polymers can absorb the most dangerous UV areas. And as I have mentioned at the beginning of the report, and this detail is able to connect atoms. Maybe there is some anti-oxide effect because of this hole. And the conclusion about boron-based polymers which prevent aging and the strength of the materials are not lowered. Thank you for your attention. So in fact, did you observe these friction changes with different boron-based acids? And of course, we would like to observe these processes on the surface. But today there are no direct methods of boron C or boron N. So the bar is the strongest. So let's continue the plenary session. I'm announcing the report of Sergei Valeryevich Konovalov, development of technology for wire arc additive manufacturing for the manufacture for fabrication of high entropy alloys. So I represent Novokuznetsk, Samara universities, as well as Tomsk University. Different teams have worked on this work. Some comparison of different manufacture stages. So first of all, additive manufacturing includes 3 stages. It's modeling, melting, and the production of the materials themselves. If we compare 3 methods of additive manufacturing, then we can get selective laser melting, direct metal deposition, wire arc additive manufacturing. We can see that SLM has advantages in the parts of accuracy, but the speed of the covering coating of the surfaces is low. The DMMD as well as WAM, the sizes of the products they have the accuracy of the surfaces, and the speed is higher than the SLM. The report devoted to high entropy alloys production. So these are the alloys that have 5 or more elements with 5 to 35% content. They have high entropy, and the 4 key effects of high entropy alloys are shown. This is the high entropy, then the nuclei that are growing slowly and severe lattice distortion, as well as the cocktail effect. There are shown statistics that we have taken from 2017. Now, of course, we have much more results, but the information more or less is the same. So the high entropy alloys are received from of the 9 elements presented here, and 4 of them are mainly used. You can see that they have the peaks. The application of these alloys differs from the type of the alloy to the content of components. So the two presented alloys are going to be defined in my report. They surely differ from one another by application. It's about hardware resistance or high temperature application or cryogenic application. Several words about the technology. So where did it derive from? The first research were discovered by us earlier. The following article is, and the article is pretty modern. So this professor from Wenzhou University was in the program. You may have heard him yesterday. So they take the wire with different components. It can be aluminum, metal, cobalt, nickel, steel. And we have taken the phrase from this article about some peculiarities of the technology. So the technology of receiving of wire takes a pretty long time, but we can get different types of alloys. And in the left picture, you can see the process itself, the process of production of bulk material. And layer by layer, you can see the process and happens, and at the end, we get the additive product. The aim of my presentation coincides with the aim of the report itself. It's fabrication of high entropy alloys of the two systems. Using wire arc additive manufacturing. So the aim is divided into 4 main stages. First is the selection of the wire's compositions for getting big volume wire. Then it's manufacturing of high entropy and the characterization of microstructure, mechanical tribological properties, and comparison of mechanical properties with the standard elements. Now, the following are the stages explained that we went through to receive the final material. So you can the different phase compounds. It's manufacturing the cable type wire, and consequently the fabrication of the high entropy alloy. Several words about the theoretical framework. So as the basis, we have taken not 5 wires, but 3 of them. And the cocktail effect has been used. Well, we have used the prostration of each element in the alloy using various formula. And this is the density of the element, diameter, atomic fraction, Avogadro number, and as a result, with the help of different thermal dynamic formula, we have the entropy of mixing. And further, we analyzed different materials, particularly having the aluminum cobalt alloys with the ferrum included. And there are different mathematical analysis for getting the ready-to-use product. And there was the relative error, but which is not exceeded to 70%. So there are many elements that disappear in the atmosphere. It's a program for AVM. We got a license for getting this aluminum, cobalt, chrome, ferrum, nickel alloy. And for the second alloy, we also had calculations. And here they're presented the initial data, the input data, output data, the results analysis, and further in China it's easier to be financially supported In our country, the situation is a little more compound. So we have created the prototype of the wire equipment. So there are 3 wires now which are applied together. So unfortunately, our production is not so huge to go to firms. The first alloy was received by using aluminium wires and the nickel chrome alloy, and then the wires that include ferrum, nickel, cobalt. So in the left slide, you can see the sizes of the wires. So on the right, you can see the real twirled wire, real image of the welding wire. And the second alloy is shown here. It's cobalt, chrome, ferromagnet, nickel, and here we have used this cross section of the cable wire, and the chemical composition of the elements are shown in the table. So you can see the video fragment of manufacturing process of the wire arc additive. There are different parameters of the process shown: the wire feed speed, the current, the speed of gas consumption. About 20 layers have been applied, and you can see the sizes. For the experimental pattern, it was enough at this stage. This is one of the fabricated samples. So the problems that we got, because of thermal effects and cooling, there were some cracks. So we fought with them, and then the number lowered. So other technologies of applying the coatings, the analysis of the results scan microscopy shows that generally there is an equal distribution of elements, but at the boundaries we can observe presence of nickel, aluminium, and the area that has been analyzed is shown in the picture. The analysis of elemental composition, you can see nickel was 34%, cobalt 5%, ferrum 17%, and chrome 8%. Generally satisfied this part of the alloy. And you can also see the energy dissociation. And they are also observed as nano-sized particles. In slide B, and there is analysis of dislocation structure. And we can see either aluminium or nickel or any other elements. And the results are published in both articles. For another alloy, chrome ferromagnet nickel. It is visible that depending on the layers of the material, we can see the division of the contacts, and the grain orientation is changing due to different thermal cycles, heating and cooling. Consequently, the orientation is changed. As well as that, unfortunately, the wires were not purely clean. There were some mixes that we cannot, unfortunately, avoid the production. And one component wires, in spite of the fact that the alloy, the given alloy is present, as well as chromium and aluminium. We unfortunately can't avoid it. So this is one of the advantages of this technology. And the thermal processes happening during the process. So there is the tension in the material and the density of dislocation. As you can see, appeared in the process. There was an X-ray analysis of material structure. So we have the cubic crystal structure with the interplanar distance 0.2 nanometers. The analysis of mechanical properties. So the material is pretty fragile, and you can see that the destruction it is seen in the picture that the experiments should be undertaken carefully. We have undertaken the analysis of some other different materials, and the properties of our material are at the same level as the other materials. The analysis of the second alloy showed us that the mechanical properties are also at a good level. The results are shown here. We have analyzed, as well as that, the micro hardness along the cross section. So the analysis was done along the whole block. You can see that micro hardness is not highly changed, so it goes quite equally. Nevertheless, the composition plays an essential role. So we can see different numbers here. So we have announced the publications, and our materials showed there are different properties. There are several publications presented. And where experiments, we have seen the mean friction coefficients are equal. But the second alloy has a higher wear rate. Some limitations that we have faced, and I would like to warn the young researchers. So first of all, it's about the quality of the cable type, of the wire type. Now, and the wire further can have some cracks, and an essential role is going to the chemical composition of the material. And so now we have difficulties with exports of materials. And the diameter is also important here. So the number of chemical compositions consequently not each wire have the pure chemical composition. And the diameter of the cable type was limited by the diameter of nozzle of the torch. So what are the further perspectives and ideas? So we have the monolith wires production, and the Chinese scientific institution also is working on it. And as a result, we have metal cord filler with a diameter of 2.54 millimeter. And this is also published already. And one of more relevant directions, it's coating of the application of different coatings with some specific geometry. So it's not necessarily a flat coating. It's an article dated by 2022. The conclusions concerning this report, what we have got from the wire arc additive manufacturing. The resulting chemicals compositions are not more than 70%, and the material structure had gone through mechanical properties. Both the first alloy as well as the second one, and the mechanical properties were compared with traditional methods. Thank you for attention. We defined the entropy theoretically. We didn't analyze it experimentally. So we will need to do that. First of all, we had the purpose to get the bulk material, and the idea was the following: that we have some partners laboratory in China and our laboratory in Russia. Thus, two teams were going simultaneously. We were getting more or less close composition materials. We're developing in this direction. So I have two postgraduates working on this topic. So I think we are at the start of this direction. At some specific parameters, we couldn't get monolith product. Consequently, the material could burn depending on the composition. And so, of course, we had to choose the gas speed, the motion speed. Could you please repeat what was the working temperature? Because aluminum and cobalt have different melting temperatures. How did the mechanical properties change, for example, strength? And what is this type of welding oriented on? And how does aluminum with its properties influence the result of this kind of welding? So the melting was in a different environment, and so there was no oxidation. And the working temperature, so it's a welding process, so the temperature was satisfying to melt the metal. It's clear that the metals have different melting temperatures, and so there is a mixture of elements, and there is a formation of monolith product. So the idea was the following: as to receive first small-sized patterns, and then to move to the bigger size patterns. So we would like, with the welding complex with a robot, to make products of big sizes. What is the innovative potential of these works? So the technology requires a lot of attention. So when can we wait for these achievements? So nowadays these materials are not widely used, but I suppose that it's coming in the near future, so we can violate the properties, adding one or another element. And we can also get material of different geometry, as well as of big sizes. So particularly, I can bring an example that in Moscow, in S7 company, where I personally was, we have a colleague working in S7. So they work with a complex of with welding technologies, getting some parts of rockets. So they give a specific geometry, they program the properties, analyze them, and the director of the company gave them a task to some year to produce a rocket. So the high entropy alloys are the alloys that have promising properties. And so there was a hope that the properties will be really high, but for now, we haven't found them yet. So generally they satisfied these parameters, but it's not, it didn't differ much. Could you please repeat again? What is the meaning of the additive word term in your context? So additive means getting a material which have large sizes, materials and sizes of different geometry. So for example, the SLS technology is layer by layer coating. Here we have layer by layer for large materials. So the next speakers, the report is about acoustic artificial intelligence technologies to substantiate the structural properties of materials. So the speaker is Olga Anatolievna Nikolaichuk. Our report is devoted to the technologies of artificial intelligence. So the general and huge tasks are production of models for dynamic technological states. These use unique mechanical systems. So why is it a unique mechanical system? Why is it called so? So we make notifications. There is a principal difference between a series of objects and unique objects. So it can give the absence of enough statistic information about this object. And in the following slide, we have tried to briefly present our model of generalized structure of dynamic technical state. So they're presenting the aspects of consideration. You can see the technical, physical, and functional states, which present the initial state to the evolutionary. So, for example, we have the sub-micro level, which develops into the state of macro level. In brackets in each block, you can see the highlighted disciplines which work in the exact research of these class state. Now to the report itself. Our report is going to include two large parts. The first is about the directions of technical stage which exist now, and the third part can be devoted to the program systems that we have already created and used for solution of our tasks. So there are several reasons for refusals, the catastrophic scale. The first reason is not identified fluctuation of the composition and parameters of properties that influence the factors of critical element. This is about non-matching and non-defining of the influencing factors. And also it's about not knowing some of the process and its characteristics. And further, it's the reason for not enough strength of the or resource of the material, the critical element, and it all leads to the catastrophic refuse. So little more detailed for each option. So we have different influential factors, chemical, mechanical, and physical. If we talk about non-defined, non-matched properties, it's about the chemical and micro and macro structure material. It's the effect of macro defects of the production, the dynamics of the material properties, the dynamic of critical elements properties, and the influencing factors themselves. If we talk about not identified factors, it concerns any violations of methods and means for production and application of mechanical objects, and it can lead to different events, processes, and states at different hierarchical levels of the structure, and defining the whole complex, we have come to some terms that should be shown in the model of technical state. First of all, it's the self-organization, and second of all, it's about the sense of initial states. So there is, when we talk about the sensitivity, there are different definitions of initial states. We also have definite and non-definite initial conditions. The definite are the project properties of the material in the technical requirements and proved by experiments. Non-identified are the practical, including not identified, which can have some defect or violations of methods and means. At the same time, there can be a combination of both conditions, and they can give us their own effect, and we have, as a matter of fact, a refusal. As a result of our analysis and experiments, we have obtained the classifications of catastrophic refusals reasons. They're all shown in the slide. On the left, you can see the stages of life cycle, and above there are shown the reasons of presence or existence of these states. And the last block expresses what we are working now, its sensitivity of initial conditions. It's quite an informative table. I think that we can go to the publication and get to know it better. So talking about the non-definition of the inflation factors and properties, there are different states and characteristics of resources. The next factor is the self-organization of the existing properties of the object. So there are many different determinations of this factor. We have our own determination. We understand it as a mechanism adaptation of object properties based on the rules which are made by the system producer. So as a result, the structure, the components and properties can be violated. As we know, in synergy there is a lot of experiment collected. We have decided that we need to make a bridge between the natural object and to show the process in these structures characteristics in order to somehow use this synergy experience for building some objects. We have some influential factors, and then as a result, as the explosion of the technical object, we have the fluctuation of properties of affecting factors. Then there is a totally new state, a change of the state. As a result, we have either evolution of the properties or catastrophe and destruction of the object. And our ideas were focused in this table, where we have tried to express the idea of synergetics. Let's go briefly to the definitions. We have the validation of properties, the fluctuation. Then the third stage is about the bifurcation, chaotic properties, and the stage of the self-organization. There is an evolution which can help to realize it or develop the properties of life. So if the explosion of the objects continued, then it works well. Otherwise, we have the catastrophe destruction. As a result of our work, we have a hypothesis. It's about mechanical objects which change their state with the same by the same reasons as physical chemical processes. We can also make the self-organization and also the resources of artificial self-organization. And this list can be continued. So what tasks can we solve based on the self-organization? So this is the defining of material, the object material properties for stiffness and resource, for diagnosing in case of catastrophes. According to these possibilities, we have defined for ourselves how we are going to improve these models. In this slide, we have tried to formulate them. Thus, we have speculated on our works and directions that we are going to work with. We want to pay attention to the sensitivity of initial objects and to realize the self-organization principles. The last part of the report is devoted to intellectual technologies, which we are using, and the three aspects that we would like to present. It's expert system, agent systems, and algorithm of self-organization. In the next slide, we will see the definitions. So the expert systems let us, based on the expert system, to get the different, we have different models of dynamic state, and it is shown briefly. It's the basis of the expert's knowledge. So in this model, we have the dynamics of revolutionary process from defect to destruction and to the refusal state. This model was more formalized in order to more logically describe the knowledge, so we can see the process gradually divided into classes of states. The processes like mechanism and kinetics and the knowledges are described as rules with conditions if then. And there are different types of degradation processes shown in the slide. Further, I'm showing examples of this expert system interface and the algorithm of this expert work. The expert has possibility to describe this model, starting from the mechanism of defect of materials description, going to the destruction and refusal, so all the stages. After description all the stages, the expert has the possibility to integrate or to predict the future of this process. Since we are oriented on not programming experts, we have thought about different mind maps, Isakov diagrams, or the event tree, and this is the tree of which describes the mechanism of one or another event. The example how can the rules look like, which describe the degradation process. The next method that we have employed is the precedent expert systems. The precedent includes the combination of the experience, and we have created the construction material choice, and we have described the properties of this material. And the materials that can be recommended to the user. In this slide, you can see the forms of requirements. And on the right, it's the solutions that the user can get with the parameters that he had chosen. There is also an algorithm of refusal analysis. They are integrated in the following system. They are devoted to different aspects and added to the model of which is based on the model of the state of dynamic technical state. Then this plan is explained, and we have the genesis of programming. And the next direction is the agent system. We have shown it with different elements, and we have opposed it to the different agent, and this agent contains a database and expert system, as well as calculating models. As a result, each agent has solved the state of its element and passed this information to the other agents in this hierarchy of the research object. In this case, it was a mechanic system. You can see the interface of our system in the following slide. There is a reflection of reason and matter model. In each of these states, you can see at any time what is the state, what are the parameters, and at the end we get results. What state can these processes bring to? And the last area that I would like to mention, it's the conceptual algorithm self-organization. In these schemes, you can see you can look at the middle part where different stages are shown. In exact case, it's self-organization of research methodology, self-organization of tasks, of analytic blocks, and the self-organization of the object properties. On the left, there are shown the sources of information necessary to self-organize and the results of each stage. So stage 0 as a result is methodology, stage 2 tasks, architecture of programming system, and the last one it's object properties. And on the right we can see this the initial data used for these processes. We have the definition of the methodology. formulate the methodology terms, tasks according to methodology, the agreement of all the definitions with the expert teams, and the saving and teaching to the algorithm to use it in the future. After defining the methodology, we start describing the definite object. So we describe its structure, give some tasks, and choose some methods and algorithms. And the third stage is solution of the tasks. And here we can get analysis of task solution results. If we don't get the solution, then we can reformulate the task, change the parameters for calculating. And of course, it's done with agreement with the expert team. As a conclusion, I would like to talk again about the self-organization method. We have enumerated what exact tasks we could solve. And according to these tasks, I have tried to enumerate the tasks that are in the field of information technologies. So it's about ontology of subject areas, working out the data of knowledge that can support the expert knowledge research, working out algorithms of methods for taking the decision, and as well as the aggregation of methods and instruments and means in the frames of technology of the digital twin. Thank you for attention. So you had two phrases, dynamic transformation and kinetic transformation. What is the difference between them? So we mean the stages of dynamics. For example, if you are researching the object when it already has deformations, then you are interested in genesis of the process. Why were these defects found out? If you are thinking about the future, then it's about prediction. It was about genesis. So in the middle of your report, I noticed some information. So what is used inside? So what kind of tasks are going to be solved in the machinery or programming teaching? So we think that it's very hard to teach to the programming. So how do you classify the combination of data? So what methods for data analysis did you use? So we have the analysis, the data analysis of content. Could you tell us, please, if there is any practical use of this self-organization? I suppose that the development of um, intelligent technologies, it can be used in informative technologies in comparison with past experience. So I think that it is more promising to realize nowadays. And so we started talking about digital twins. This is what we meant, combining different technologies in frames for one system. When one team works at development of one object, so they are trying to describe from different aspects the object that they develop. So we think that there is the evolution stage when we come back to theoretical works with a new view, with a new realization. So usage of the self-organization principles it hasn't been realized by us yet, but we set the tasks and we have mentioned it in the report, and the realization to define the properties. We hope to employ it in the near future. And the next report, Oleg Viktorovich Bashkov from Komsomolsk-na-Amure State University. And the topic of the report, acoustic emission during deformation and fracture of polycrystalline and composite materials. Good afternoon, dear colleagues. First of all, I would like to thank for this opportunity to speak, to present my report. I would also like to give you a brief story. So it's the information who has just started working with this acoustic emission method, and for those who are pretty deep into it. So this acoustic method is well known since the middle of the previous century. The researchers had heard about it at the beginning of 16th century. They have heard about monocrystalls like zinc, and it was taken like some effect. And the research in the area of application of this effect was done later, and it was widely used in the 60s, 70s centuries of 20th century. When the NASA started researching deeply, and they're trying to choose the diagnosis method. And it was financially supported later on in the Soviet Union in the 70th century, 80s, in the 80s of the 20th century. So there was an article published in 76 year, the monography Acoustic Emission, which included a complex of results of foreign as well as Russian scientists' research. And in Komsomolsk-na-Amure, it has been developing since then and until now. And now we are actively presenting this direction. So wide usage of acoustic emission was gotten and is used at the present time to control the processes of experimenting the different bulbs and different equipment and railway trolleys and platforms. And as a result, no one wagon had any crash after undergoing acoustic emission. So fortunately, the objects which undergo acoustic emission, it helps to avoid any crashes. Thanks to integral assessment of the object in a whole, there is a possibility, the method of registration of the wave and the local transformation in general, there is difficulty in setting of a big number of controllers. So except the development that we have the control of parameters, there is structural deformation of the grid, and there is the outer influence, not only mechanical but also thermal influence. So it helps to get the indirect information. And taking into consideration that acoustic in acoustic, a lot of knowledge was devoted to mathematical description of acoustic waves. It led to use the definite method to divide, to classify them according to the character of the waves. And it's the resources of plastic deformation, of distraction. It's also dislocation effect, twinning. And if we talk about distraction, it's surely different scale of crack formation. In the standard, it's given that the sensitivity of the method of classical emission, it's formation of cracks and formation on some surfaces, which is high sensitivity, which allows to undertake research in frames of quite good equipment. So including the parameters, the information about parameters of acoustic wave, there exists quantity and energetic dependence, and it can be described by some relation of frequency and energy. So there was suggested some frequency parameter and numerous research works have led us to say that there can be done a division of the emission sources according to the types of registered signals. So we can see the field with the energy and frequency parameter. And here we can see that the signals with some low ratio of frequency parameter is registered with a multi cracks as well as the micro cracks, and the other type is macro cracks. And you can also see the twin cracks. And at the stage of um, elasticity or micro deformation, there can exist at the edges of the grains. So further was information about dislocation of cracks which go out of the surface of crystals. They may do it, but the level of register signals are lower. Thus, further we have the active plastic deformation at the beginning, and it can be registered as a signal of acoustic emission. The research of aluminum deformations, alloy deformations, we can see the different stages of the fluidity, and you can see different zones of deformation. Obviously, when they appeared, you can see a sign of the classical deformation. So these are the signals registered by us. They in the past they didn't have any equipment which we do now. It's essential to see the information which was get at the different cycle experiments and testing. So it is tightly connected with analysis which was done in the 70s, and these results allowed to form some diagram of the cycle awareness, And this all is tightly connected with the difficulties of analysis. And every time, at every stage, one needs to make the pattern. And at different stages, different signal types can be registered. And in acoustic emission, they can also be defined. So we have the titanium alloys, aluminum alloys, which let us show that the um, generating diagrams have equal numbers. The signals of plastic deformation show that at the stage of cycle um, um, of cycle strength. And the next one is a crack formation, which goes quite closely. As well as that, the research allowed us to define that there is some structural differences. So we can have macro crystallized structure, ultrafine grain structure, as well as micro crystallized structure. So you can see the essential difference, these three structures. So there are much more signals of macro crystallized structure, which is obvious since the level of the signals is quite lower. So it doesn't mean that the signals are not registered. They are, but they are the level of the acoustic noises. And so if we try to analyze the stages, the main task is the possibility of early diagnosis in order to be able to predict. So in the macro crystal material, as an example, there were the patterns in the undertaken by Yuri Petrovich Arkeyev. He showed that you can register about 24-25% until the end of validation of the pattern. And if you go to the ultra micrograin structure, then the percentage is really low. And we could go thus to the conclusion that any class of group of materials can reduce the volume of fractographical descriptions at different stages, and of course it requires testing on different levels of attention, which will allow while testing one pattern or not a big group of patterns to identify the properties without stopping it. Now going back to the fact that the wave which is spread in the object can go through transformations. And if we are talking about spreading a wave in some objects, most objects can be described as plates or some roots. So it's a cylinder type plate. And a well-known fact about the dispersion of sound wave signal, there can go along the plate or across it. So there was shown that there is presented the curve of dispersion of group speed. It's symmetrical and anti-symmetrical waves. Consequently, we see that the wave in some particular state can change essentially, but we still can't draw conclusions about some transformations which could be described in numbers. So it was received later on. You can see the research, the patterns of different hardness. So trying to combine the distance and the properties of the distraction objects. They have got the results which allow to receive the dependence on hardness. Basically, it's the properties of the source and the distance of some poly dependence. Furthermore, there was license got on this method. Later on, it was tested on the real patterns, and in the process of wear growth cracks, it is constantly moving. And at this point, there was a setting, and it provoked the growth of the crack, and it led to the situation that we have the dependence that the distance along the crack, when it got the growth when and the wear state, and there is another parameter, the hardness, which is reducing. And there is a relation of two energies which were obtained by low frequency component and high frequency component of signals of the fourth stage. It was about 300, 400 kilohertz. there are shown the pictures where the future where crack was going closer and closer to its destruction. And just one or two slides about acoustic emission at destruction of polymer composite materials. So there is the possibility of division of the signals of emission. And there is the Fourier spectral used there, and the complex analysis showed that now you can't go without global split of neurons. And the combination of analysis let us identify the defects of fibers, and to be able to describe it. And I would like to also present some last research results. So we can suggest a new controller type. It's fiber optical controller. So there are the Brett's controllers. All in all, its low sensitivity doesn't allow to control any light or low amplitude oscillation, and according to the principles of there were different measurement systems that allow to structure the material with the help of the fiber and to use them to control the acoustic changes. And using it's about the stabilization at the working point based on photo reactional and some frequency pressure of waverings. It led to the formation of a multi-channel system where even single crystal can be used. These are not our data, but data got from the Institute of Vladivostok. But as a result, we have installed the controllers and composites. Now we glued metal plates to have the possibility of registering the compound forms of waves, which are shown on the left. And this is the signal obtained from the different crystals and optical fiber. Nevertheless, the formation of grind can allow, as a result, to effectively use it in order to have an opportunity to have a system of constant system of monitoring. Thank you. So the question is, how can this data be used in practical sense? So the criteria that I have mentioned are given in the standards, and they haven't been changed around 30 years. And presenting new criteria require a lot of hard work, and I am taking part in the team working with efforts, and we are trying to include the last 20 years experience and knowledge, so it is in the process. In fact, I have shown a new type of controllers. The whole fiber is sensor, and you can use it in different ways on the object. And the bigger the sensitive area that takes the acoustic waves, the more signal we will get. And if we are talking if we are talking about non-contact one, then we have a lower level of signal, so the sensitivity is not enough. Do I understand right that you start registering the signals in the area of microplastic deformation? So what pressures are they? What strains are they? How do they concern the cycle strain? So what kind of strain it is on the microscopic curve of load? Some materials start giving opportunity to register the acoustic signals. Let's say about 5–10% of proportional border. We know their methods. The Professor Vinogradov method is the registration of analysis like non-continuous stream. And here we work on the borderline level. So we present each signal as a particular single acoustic emission, and it is considered its frequency and energetic parameters. Each method can be researched and can exist. Of course, we are aware of other methods.
Посвященность должна быть в пределах 10-15%. Надо сказать, что посвященность получится более-менее. И ударная вязкость. Ударная вязкость есть определенные проблемы, о которых я, в общем-то, как его скажу, по нормальным современным представлениям ударная вязкость должна быть не меньше 30 джоулей, чтобы материал, в общем-то, был, так сказать, можно было эксплуатировать. Но испытания есть с П-образным надрезом. Это у нас в России там делают П-образный надрез, чтобы, так сказать, получше данные получить. И, естественно, испытания хорошо бы делать при минус 40 градусов. Считается сейчас стандартная температура, не потому что там везде минус 40 градусов, а потому что она гарантирует, что, собственно говоря, везде сталь можно применять.
Вот. Кроме того, существует класс стали, который создан на базе который упрощается дисперсионным спердением. Там добавляют к ним в обычный состав, это, конечно, сталь чуть подороже, необий молибден, ну, в очень небольших количествах, необий добавляет там в пределах 4%, процентов молибден чуть побольше там добавляет, и там уже можно, значит, говорить там больше предупреждений. Конечно, на этом графике изображено 2400 МПА, значит, предел прочности или временный, значит, разрушения. Ну, конечно, таких значений получать пока не удается, но, скажем, там 2000 это вполне реально. Реально, это предел текучести будет где-то 1900-1800. Ну, так сказать, там пока не очень удается, но 1700 у нас пока получается. Это, естественно, дело, еще раз повторяю, все проблемы в этих стадиях не то, чтобы получить какую-то рекордную прочность. Кому рекордная прочность, она, в общем-то, не нужна. Самое главное, чтобы при этом было относительное удлинение, то есть и ударной вязкости. То есть, как я сказал, вот 30 джоулей – это вот такой порог, который мы должны выходить. Или там, в общем, не выходить. Но это другой вопрос. Теперь принцип этих сталей. Он чрезвычайно простой. Это вот здесь график. Здесь Рауса хорошо, значит, видно. Он вот все стали делиться там на два типа, грубо говоря. Меньше 0,5% углерода пышный. Если меньше 0,5% углерода, то можно обработать на то, что у нас называется низкоотпущенный амортисит, low temperature site, и получить свойства. Как получается свойство? Значит, у нас получается пакет амортисит, обязательно пакет, никаких других вопросов там нету, значит, амортисит мы получаем, и в нем должен быть остаточный аустенит, да. Вот, это должен. И вот прошивки остаточного аустенита, они должны обеспечить нам пластичность. То есть у нас удар получается, в принципе, нормальный, там, значит, 30, 40, 50 джоулей получается, и, в принципе, такой материал можно эксплуатировать. Вопрос существует, чтобы надежно воспроизводились эти данные, и чтобы все-таки, так сказать, сталь была, ну, скажем так, более-менее распространена. Вот в этом графике хорошо, значит, видно. Сталь, значит, я вам сразу могу сказать. Вот если сталь по 30, это стандартная сталь, система, значит, промолибден, почему-то до сих пор, значит, вот в нашей стране ее нету, ну, в смысле, как точно такого химического состава, как сталь 40-30. Здесь, если мы, значит, если в градусах Фаренгейта, но я могу сказать так, что где-то вот если 250-300 градусов ее, значит, отпускать, то вполне получается нормальный удар, и, значит, получается, значит, предел текучести примерно, значит, 1200-1300. То есть МПА, и с этим, значит, эта сталь, значит, эксплуатируется, она вполне нормально, значит, проходит, работает, значит, очень широко распространенно, но вот, скажем, только я работаю в аграрном университете, у меня всегда, значит, вопрос, с каким тест-объектом сравнивать. Но когда я сказал, что в нашем мире сравнивать со сталью 41-30, на меня сделали, сказали, нет, у нас сталь 30 как я говорю, хорошо, ладно. 41-30 была изобретена в Америке, не изменяет, в 1932 году, хорошо, 30 как это немецкая сталь, значит, ну, по-моему, 1908 года. А рождение, ну, хорошо, давайте сравним с 30 как так, ну, так сказать, там 25 лет разницы, то есть стали уже в бою, то есть не в бою, там в этих использовании уже 120 лет. Ну, в смысле, ее в первый раз используют для этих круг провансалевых, значит, Первой мировой войны еще, для самолетов. Вот, поэтому, ну, скажем, для промышленных этих углов применяют, так что можно сравнить с 30 веса, ничего там такого нет. Дальше. Переходим к вопросу, как, в принципе, значит, что такое, значит, Machine Partition делается очень просто. Делается обычная закалка, ничего тут такого ничего сверхъестественного нету. Значит, мы закаливаем до определенной температуры. То есть не какого закаливаем какому-то, а определенной температуры. 200, 250, там, 150, ну, в пределах где-то 180, 280 градусов. Вот. Вот так. И потом делаем partition step. Значит, когда делается, значит, разделение. Сейчас я скажу, что это такое. Значит, partition step бывает равен температуре закалки, бывает чуть повыше обычно. Ну, значит, больше 400 градусов мы не повышаем. Это я вам тоже расскажу. Вот такая красивая картинка получается, синенькая. Можно, значит, вниз картинку посмотреть. Здесь самое главное, чтобы у нас образовался ус. И, собственно говоря, весь вот многоструктурный дизайн этих сталей сводится к тому, чтобы мы выделили снит в виде этих, в виде пленок, каково по границам блоков или по границам, значит, арей. Но если, значит, появляется в виде таких вот крупных частиц, блоки Аустнайт называется, по границам исходных Аустнайт зерен, ну, хотелось бы это делать. Вот. Соответственно, значит, нам нужно решить вопрос для получения нашей ситуации. Это вопрос, что фаза аустенита должна иметь равную прочность фазы композита. Вот, собственно говоря, то есть это основная задача, которую мы решаем на стадии партишн. То есть на стадии квенчик, то есть на стадии закалки мы получаем наш аустенит, как я потом скажу, что где-то примерно 10% мы должны его получить. А на стадии партишн мы должны получить так, что прочность аустенита равна прочности. Все. То есть мы получили, дальше у нас все хорошо, прочность у нас есть, сигма 2 у нас есть. А если, значит, прочность аустенита будет маленькая, то сигма 2 у нас тоже, значит, будет начнет скакать, то есть деформация начнется, и начнет деформироваться слабенький аустенит. Поэтому представлена прочность, скажем, магнетита, значит, это известная, значит, формула, так сказать, там не вникая, значит, в их, значит, рассмотрение, просто, значит, я хочу обратить внимание, что вот, если мы берем процент, значит, углерода, то там, значит, нам нужно умножать на коэффициент 5544. Там есть, значит, вопрос, что будет, скажем, коэффициент 3500 взять, там, значит, под корень взять 100% углерода, там, ну, по-разному, где подходит. Но, в принципе, сами все понимают, что это измеряется там тысячи. Вот. Дальше, значит, структура амортисита понятна. Тут я могу сказать одно, что структура амортисита достаточно нет, там по количеству дислокаций она примерно, значит, там одинаковая. Единственное, что там, значит, есть вопрос по толщине амортиситных пластин, но это уж, ну, как говорится, ухитриться надо на задаче, так сказать, разработчиков стали, то есть наша задача, и чтобы сам размер аустенита был, ну, потоньше даже магнетит, потому что в случае мы даже выиграем в упрощении за счет размера зерна. Вот теперь, значит, осталось тут все можно пропустить, и, значит, это замечательно, самое главное, что содержание углерода умножается на 356, то есть мы получаем сигма 2. И мы понимаем, что у нас вот 10 раз разница. Вот. 10 раз разница у нас есть, и, грубо говоря, соответственно, из этого, значит, небольшого рассмотрения, значит, вытекает постой и, в общем-то, важный вывод, что каково нам нужно, чтобы у нас разница в содержании углерода в аустените и магнетите была примерно 10, ну, плюс-минус, может, там, 12 и так далее, но это не важно. И еще если есть вопрос, что вот если, скажем, мы выделим частичку, мы его можем добавить сюда, так сказать, дисперсионное упрощение, там частички выделяются, когда не когерентные, поэтому я поставил уравнение Арова. Ну, там есть варианты, я вот говорить не буду, но, в принципе, самое, значит, тут в 90% случаев будет тут как-то. Если, скажем, у нас и нет возможности, так сказать, что-то там сейчас получить, ну, вот будем использовать, так сказать, 5-6 нанометровые частицы неофициальные. Вот. Теперь задача стоит вопрос, как, собственно, нам, что нам делать с аустенитом. Вот тут я сразу могу сказать, что сделать нам тут особенно ничего не нужно. Вот как нам нужно так закалить, что у нас было 10% аустенита. Примерно. Вот. Поэтому в каком-то закалке это замечательно, но там получается 2, 3, 4%. То есть, ну, в общем-то, не хватает. Но иногда и хватает. То есть это уже вопрос от того, значит, какие требования к ударной вязкости предъявляются. Теперь, значит, мы закалили, и когда вот мы закаливаем, тут, собственно говоря, количество углерода в аустените будет точно такое же, как в магнетите. И дальше начинается стадия партишн. Мы должны, значит, этот углерод перекинуть из магнетита в аустенит, чтобы, так сказать, у нас разница была, как я сказал, 10 раз. Вот это наша цель. Она простая, ясная, понятная, вопрос, как вы видите. И почему она реализуется, кстати говоря. Вот. Здесь вот есть исследование, что на самом деле происходит разделение аустенита, что это вполне, вот показывает график, достигается, что вот эта 10-кратная разница появляется. Скажем, грубо говоря, мы получаем в магнетите, ну, так сказать, 0,1%, а в аустените мы стараемся получить примерно 1,5% углерода, и в этом случае у нас получается равнопрочная структура, зависит, конечно, от состава стали, и, соответственно, мы, как мы говорим, что механические свойства не получим. Вот это основа физической методологии, quantum partition skills. Теперь вопрос, физическая часть. Значит, а почему там происходит какого разделения? Ну вот здесь скажут, вот термодинамическая, так сказать, то, что называется по-английски equilibrium ситуация. Вот, аустонит, как того, находится в равновесии с ферритом, там все понятно. И должно быть нормально, значит, такое вот термодинамическое равновесие, что вот какого там 200 градусов, там аустонит должен распасться на карбиды, да еще превратиться там, в пенит там, или там какого, ну, феррита не может превратиться, ну там, короче, самого в фазу Сузагаришев. Теперь возникает вопрос, что нам тут делать? Мы, это превращение мы его так берем без зачеркивания. Зачеркиваем не значит, что мы его зачеркиваем, значит, мы залегировали так сталь, чтобы это превращение не шло. Ну, сталь специально легируется, значит, поэтому основные легирующие элементы марганец кремний, чтобы, значит, нам подавить, значит, equilibrium transformation и, значит, перейти, то, что называется para-equilibrium transformation. Это когда у нас что такое para-equilibrium transformation? Это когда у нас не происходит разделение по элементам замещения. То есть вот марганец. Мы ввели 1% или там 1,5% вводим в сталь марганца. Вот в андесите будет 1,5% марганца, и в аустените достаточно тоже будет 1,5%. Это то же самое с кремнием. Там будет по 1,5%. Он каково равный. Теперь вопрос, каково, так сказать, сходится углерод. Хорошо. Вот температура, она ограничивается от нашего партишн от 200 до 400 градусов. Когда вот мы можем выдержать условия пары эквилибрия. Или, по-русски можно сказать, ну так, условия недостабильного равновесия. Пожалуй, это будет справедливый перевод, хотя бы уже совсем физический смысл его достаточно точно. Значит, мы сталь, она какого происходит вот partition в условиях, это называется по-английски constraint equilibrium. То есть это, ну, скажем, так сказать, я не смог придумать русского слова, я думаю, чтобы это начать перевести. В принципе, оно сводится к тому, что химическая энергия углерода в аустените и какого мордесите, она должна быть одинаковой. Вот это хорошо показано. Ой, значит, вот две кривые с касательным строем, и эти касательные должны в одну точку, значит, углерода попасть, и вот если они попадают, у нас получается условие констант какого параклита. И наша задача, чтобы эта точка была таким образом расположена, что вот эта разница была 10-кратно, там 15-кратно, ну, 10-12 раз достаточно. Теперь тут вопрос, какого статистические расчеты были выполнены, там вообще получается разница очень хорошая, но статистически тест попадает с тем, что есть. Здесь вот хорошо написано, что 200 градусов получается там в 10 раз, а получается там 55 раз. Ну вот, в следующий раз с комментариями мы, конечно, не наблюдаем. Мы и 10 раз наблюдаем, значит, это очень сложно наблюдать. Вот. Поэтому мечты у нас одним, реальность другая. А когда, скажем, температуру 400 градусов поднимаем, то разница сходится там 1000 раз разница. Это теоретический расчет. Практически так не получается. Вот. То есть вот эта теория. Соответственно, каково, она исходит из того, самая главная теория, что мы подавляем полностью термодинамического равновесия. И с этим ситуация, значит, более-менее понятна. Так сказать, каково, это нужно подавить выделение карбида. То есть основная задача вот, состоит в легировании этой стали, то есть это поделить выделение карбида. И ее нужно решать любой человек. Потому что если начнет выделяться карбида, то на этом кончен partition стил закончится. То есть стремитель мы даем легко. То есть там, чем больше карбидем не ввел, тем, значит, лучше значит, с этим ситуацией. Так сказать, тут схема показана, что вот как это сделано. Вот, значит, закалили у нас аустенит, ему носит содержание равно содержанию в металле этих элементов углерода, а потом самое начинается, значит, магносит становится меньше углерода, а снизу становится больше. Вот. Теперь я так смысл свой проживал. Вот, мы вводим, значит, как у кремния, и мы подавляем. Значит, к сожалению, там еще помимо того, что цементит выделяется, что с ним бороться хорошо, так сказать, легко и просто. А вот там выделяется еще эпсин карбид, с ним, так сказать, придется очень хорошо думать, там придется балансировать марганцем и другими химическими элементами, потому что цементит не очень эффективен против подавления эпсина карбида. Ну, тут уж, как говорится, от искусства зависит, что можем, то и делать. Дальше. так сказать, вот картинка замечательная. Картинка, значит, показана, что хорошо. Мы, то есть время partition, оно там вообще в секундах измеряется. 5 секунд, 10 секунд, там 30 секунд, это вообще уже, если можно сказать, очень много, а там 1000 секунд, это можно сказать, уже вечность. Вот, поэтому вот такие технологические процессы, они идут быстро. И вот наша задача выделить достаточно нет по границам какого блока. Тут он такой достаточно толстоватый получается. И наша задача получить, потому что нет толщины 50, условно говоря. Здесь, так сказать, не всегда получается хорошо, это изотопные данные, наши данные. Вот, но мы, конечно, стараемся потоньше. Теперь, все же, что мы, так сказать, хотим получить? Мы хотим получить толщину от 8 до 12% мегаваттов, вот, 8 нормально. А это зависит от того, как мерить. Значит, к сожалению, и бездимер, и рентгеновский метод, они дают разные результаты, но это ничего тут не сделаешь. Это у всех так. Содержание углерода в остаточном слите я вам уже сказал, что получается в реальности экспериментально наблюдаем от 1 до 1,5%, но мы стараемся, надо стараться получить 1,5%. Теперь здесь показаны распределение, значит, какого аустеница как по объему, так и по, значит, содержанию углерода. То есть, с нашей точки зрения оптимальное объема остаточного слита 8%, оптимальное содержание углерода в нем 1,5%. Если получаем, то у нас будут свойства. Вот. Какие, значит, существуют схемы, так сказать, какого исполнения, значит, quantum partition treatment? Ну, схем, в общем-то, как бы 3. Первая схема самая простая. У вас температура и закалки, и партишенка, она одна и та же. Вот, 280 градусов скалили, очень хорошо, и 280 градусов выдержали, и, так сказать, и время хорошо регулируется, и температура закалки хорошо регулируется. Вот, ничего не надо менять. Но она, там есть определенные моменты, что вот это хорошая обработка, но для стали там 0,2% углерода. Да. А вот когда стали по другое содержание углерода, по площади, там чуть-чуть, так сказать, это дело не проходит. Там нужно разную температуру иметь для какого закалки, ну, здесь, скажем, показано для закалки температура, и, значит, для партишн. И есть еще третья обработка, когда, скажем, партишн выполняется, скажем, ну, там 330 градусов, потом еще делается старение, там, отпуск старения, или, ну, для кого-то отпуск, для кого-то старение, для этого отпуск, и выделяется энергия. Но выше 400 градусов перегревать нельзя. То есть вот это 400 градусов очень опасно. Там, не дай бог, другие карбиды выделяются. Вот здесь хорошо видно, что вот, что нам нужно, вот выделяется прям-лайк. Это достаточно нет, но иногда все у нас появляется, ну, тут уж ничего не сделаешь, будете установить, ну, какого стараемся избежать, специально регулируем, и тут других способов нет. Вот такие, значит, существует схема термической обработки. Понятно, что нам нужно. Значит, в чем проблема очень серьезная? Проблема очень серьезная в том, что когда мы основной следующий метод, если мы кремень не ведем, то у нас выделяется карбид. Некоторые пытаются ввести, кроме кремния, еще алюминий, тоже подавлять выделение карбидов. Но вот лично я подумали, значит, поломали голову, решили, что мы одновременно кремний с алюминием ввести не будем, потом по металлургическим проблемам. Это такая проблема при выпуске, что, ну, так сказать, лучше остановиться на каком-то одном. Или кремний, или алюминий. И все-таки по quantum partition сил мы остановились на кремнии. То есть по другим материалам мы купили алюминий, значит, там высокомарганцевых, а вот здесь кремний, там по другим причинам, значит, вот. В чем тут проблема? Проблема чрезвычайно простая, что вот введение кремния, водителей приходится много, вот здесь показана вот температура кубоковязкого прихода, то есть если 1,5% кремния ввели, то у вас температура кубоковязкого прихода увеличилась там на 60, на 65-70%. И, соответственно, у нас возникает другая проблема. То есть пластичность стали замечательной, в осудлением у нас вообще никаких проблем нет. Но ударная вязкость получается, ну, скажем так, не очень. Тут ничего не сделаешь. С точки зрения того, что сделать ударную вязкость, остается вот этот член. Сейчас, значит, не буду много про него говорить. Принцип простой. Нам нужно уменьшить размер, значит, зерна, которые ответственны за хрупкое разрушение. Вот. Других способов значит, понизить температуру Фукуямского перехода нет. Вопрос один, что такое размер зерна в морфоситной структуре? И ответ на него тоже чрезвычайно простой. Это размер. Вот. И поэтому значит, возникает вопрос, как управлять размером пакета. Это значит, отдельная тема, отдельный интерес. И, собственно говоря, значит, выясняется, что значит, если мы хотим гарантированно подавить выделение значит, карбидов при партишинге, то значит, что-то нужно сделать с размером пакета, иначе у нас ударной вязкости не получится. Вот. Тут значит, такие вопросы. Тут дальше указано, что мы тут маргинс вводим. Ну, маргинс мы дальше вводим. Ну, значит, там получить управляемую сталь, чтобы значит, не бегать. И поэтому значит, маргинс не дергаться с температурой, мы ввели. И у нас более-менее эскривы ушли вниз, и мы ими можем управлять. Ну, а там фронт тоже дает нам прокаливаемость, а не бессмысленно, конечно, упрощение. Теперь, здесь показано примерно стали, примерно какие свойства, значит, как мы получаем. Вот, пластичность там, пластичность получаем численность нормально, то вот старом пока 28 джоулей получается иногда, получается, но в принципе мы на 200 прав. А вот соотношение сигма-б умножить на дельта, который характеризует энергию пластической деформации, когда у нас не образуется трещина, то есть мы гарантированно получаем даже больше ключей. Ну вот это все, что я хотел сказать. Спасибо за внимание. Теперь можно перейти к вопросам.
Спасибо. Давайте благодарим. Вопросы, пожалуйста, к докладчику. Все устали перед обедом. Да, пожалуйста. Да, здесь.
Меня интересует вопрос закалка на небольшую глубину, типа вот импульсным вбросом энергии. Вот как насчет этого обстоят дела?
Я не очень понимаю, значит, зачем закалывать. Мы нагреваем в обычной печи, мы прогреваем, у нас, собственно, нету такого лимита по прогреву под закалку, то есть у нас мы прогреваем весь материал, зачем там импульсные вещи. У нас проблема при охлаждении, то есть мы должны обеспечить достаточно высокую прокаливаемость стали, но с другой стороны, когда значит, вот таком легировании примерно и до 1,5 марганца, то есть тех объемов, которые там используются для сельскохозяйственных инструментов, мы прокаливаем на 100%.
Следующий вопрос. Там есть, да? Вопрос? Да, пожалуйста. Несите, пожалуйста, микрофон.
Скажите, пожалуйста, вот столь малая временная термической обработки, они накладывают какие-то ограничения на размеры, на массу изделия, потому что, ну, она или на равномерность, неравномерность прогрева?
Ну, в принципе, да. Но тут нужно, значит, понять назначение изделия, потому что вот у нас, скажем, лемеха плугов, они там, ну, где-то там 8-12 миллиметров максимально. То есть вот когда в таких пластинах от 8 до 12 миллиметров, то, в общем-то, все получается там в пределах 100 секунд, и там, ну вот, насколько мы пытаемся, то есть, ну, у нас все физиратуры, никаких проблем там. А когда там, если думаете, там 30 миллиметров, это там могут быть вопросы, но это уже другая, значит, задача, она по-другому формулируется, и, собственно говоря, потому что вы должны понимать, любая сталь с пределом текучести свыше 1400 МПа, эта сталь называется высокопрочной. Если мы там получаем там 30, 40, 50 джоулей, то ее можно использовать высокопрочную на замену стали 300 КПМ. Ну вот там, да, там возможно вариант, тут даже, вот, насколько я знаю, как они используются, там тоже никаких 30 миллиметров нет, там толщины тоже будут делать 10 миллиметров.
Есть еще вопросы? Нет, да? Ну, давайте еще раз поблагодарим докладчика за интересный доклад. Спасибо. На этом пленарное заседание завершается.